So let us talk about logarithms. Mostly we're going to be talking about how to graph them, but it still does require a little bit of buildup. So the logarithm equation I always think of when I am thinking of how a logarithm works is the following one. 2 to the third is equal to 8 means the same thing as log base 2 of 8 equals 3. So when you see this, I really, really do encourage you to say the words, as you know I do, log base 2 of 8. Don't just say log 2 8 or log 2 of 8. Really say log base 2 of 8. Because when you say that it's base 2, it's a reminder that, oh yeah, we have a base of 2 and it's being raised to a power. What power? That's what we're trying to find. So when we read log base 2 of 8, what I think is 2 to what power is equal to 8? So I should say 2 to what power is equal to 8, right? I go from 2 to 8. How do I get there? Well, I know that the answer is 3. 2 to the third power equals 8. So log base 2 of 8 equals 3 exactly because 2 to the third power equals 8. And that's very much how logarithms work. So I wanted to give you all an opportunity to find log base 3 of 81. And I'm going to remind you, what are you trying to find? You're trying to find 3 raised to what power equals 81. It's a nice whole number. Anyone want to tell me in the chat what it might be? Exactly. You guys are on top of it. It's exactly 4. And the reason it's 4, you guessed it, is because 3 to the 4th power equals 81. Yeah, let's see. So I have a whole other page here that I've already written just because I wanted to write a couple things ahead of time. Because you know, I'm not the fastest writer all the time. So more generally, if you have y equals some base to some power, b to the x, that's equivalent to log base b of y equal to x. So log base b of kind of the outcome is equal to the exponent. And the reason I wanted to mention this is because a lot of times you might hear someone say a logarithm is an exponent. And the reason they're saying it is because it literally is, right? If we're thinking about y equals b to the x power, if we're trying to find log base b of y, it's really just equal to the thing that is the exponent, so that b to that power is equal to y. And that's kind of the whole deal. I wrote some things here, right? People say the logarithm is an exponent. Log base b of y is literally the exponent. We raise the base b2 so that we get the value of y. So not that I really want you to worry too much about this, but it is also true that if you replace x with log base b of y, it is really, really true that b to the power of log base b of y is equal to y. But that's kind of an aside. Also, I'm getting a million text messages. I feel like I should look at my phone. Okay. That's cool. So something else I wanted to point out, log base 3 of 9 is equal to 2 because 3 raised to the second power is equal to 9. And I just want to help you avoid the pitfall of thinking that log base 3, maybe not thinking, but accidentally writing that log base 3 of 9 is equal to 3, right? It's not. Yeah. And so I would, as someone saying never learned this before, didn't know this is straightforward, I'm happy to hear that. I definitely, when I learned logarithms the first time, I really did struggle with them because this inverse relationship that they kind of have is very challenging, or was challenging to me the first time. But eventually it made more sense when someone explained it in a more straightforward way. So yeah, I just want to point out, right, this is not equal to 3 in a similar way. Log base 2 of 8 is not equal to 4. Right? We're not looking for the thing that you multiply the base by. Right? 2 times 4 is 8. 3 times 3 is 9. We're not looking for that. We're looking for the thing that you raise the base to as a power. 3 squared equals 9. And that other notes. Right? 2 cubed equals 8. So when I'm looking at this, I'm always thinking, oh, this base. In fact, I often write this. I'm like, oh yeah, this base raised to this power equals that. I kind of think about starting at the base, going over here, going back over there. And I think it's worth mentioning, this is in fact very similar to how the inverse trig functions also work. So I'll remind you guys, and it's been a little while, sine of pi over 6 equals 1/2 is, I won't say 100% equivalent, but essentially is very similar to saying the inverse sine of 1/2 is equal to pi over 6. And because when you're trying to find an inverse trig function, this inverse trig function of 1/2, right, you're looking for the angle that if we take sine of that angle, we get 1/2. What angle is that? Oh, it's pi over 6. Now I know with trig functions, there's other angles and it's a little bit more nuanced, but we're not going to worry about that. The same thing is true with exponential and logarithmic expressions, right? Writing 5 to the third power equals 125 is equivalent to saying, oh, log base 5 of 125 is equal to 3. Because just like the inverse sine of a number, you're trying to find the angle that if you took sine of that, you get the number. The logarithm is the same thing, but for exponents, right? We're looking for not the angle, but the exponent. That if we raise the base, 5 in this case, to that exponent, we get 125. That's it. I'm going to write this thing down again. I know I already wrote it once. I'm going to write it one more time. At least log base b of y equal to x is equivalent to b to the x is equal to y. By the way, that's what these double arrows mean. It means that this thing and this thing essentially have the same meaning. They're just maybe different ways of expressing it. And again, if I was looking at this, I'd be like, oh yeah, b raised to the x power equals y. That's how I always kind of look at that. Okay. We're not going to talk about any of the real rules of logarithms. That's for another, not this class. But we are going to talk about how to graph logarithms because that's kind of, I mean, excuse me, all the things are important. That's what we're going to spend our time on today. Now, the nice thing about graphing logarithms versus exponentials is we're really just interchanging the role of x and y. So let's look at some examples. Let's see, graphically, logarithmic functions are just exponential functions that we talked about last week with x and y interchanged. Let's go back to kind of our first example of an exponential function. So when we graphed y equals 2 to the x, we plotted some points, and they were these points. We had x being -3, -2, -1, 0, 1, 2, and 3. And the y values were 2 to the -3rd, which is 1/8, and then 2 to the -2nd, which is 1/4, 2 to the -1st, 2 to the 0th, 2 to the 1st, 2 squared, and 2 cubed. And we plotted those points. We got some stuff, 1, 2, 3. So kind of like this. And again, I'm not trying to be super extra duper precise. I'm just trying to make it look kind of nice. Sure. So that's how y equals 2 to the x looks. Now, if I want to graph y equal to log base 2 of x. So now the x is playing the role of the the y is playing the role of the exponent, right? So here, right, x was the exponent, -3, -2, 1, -1, 0, 1, 2, 3, and the output was what we got over here. Now the previous output is going to be the input. and the new output's going to be the output. They're switching, or in other words, we're finding the inverse function, because the inverse function is what you get when you interchange x and y. All right, so and I should point out, right, you could rewrite this if you wanted to, right? You could rewrite this as 2 raised to the y power equals x, which is just that with x and y interchanged. So it literally is the inverse function. We can also plot points. And yeah, sure, I've got room here. So whenever someone asks you, what kind of value should I pick to take the log base whatever of? The right answer, and meaning the answer that's going to be the easiest, is you want to pick things that are easy to take log base 2 of, meaning you want to pick powers of 2. So I'm going to pick something like 8. And then y is going to be log base 2 of 8, which is 3. And something like 4. And log base 2 of 4, well, 2 to what power equals 4? Oh, 2 to the second power equals 4. And 2. Log base 2 of 2 is 1, because 2 to the first power equals 1. And 1, because log base 2 of 1 is 0. Right, 2 to what power equals 1? Oh, 2 to the 0th power equals 1. And you can keep doing this for any positive numbers. But we're going to pick, right, nice powers of 2. 1/2 is 2 to the negative 1. So log base 2 of 1/2 is negative 1. And 1/4 is 2 raised to the negative second power. So log base 2 of 1/4 is equal to negative 2. If you have questions about what I've done here, now is an excellent time to ask them. I'm going to graph this, but chime in with a question if you have one. So x is going to go out to 8. And then I'm going to get the 0.83, the 0.42, the 0.21, the 0.10, the 0.1/2 negative 1. It's going to look like this. It's all right. So something to be aware of here, which is a nice fact, is that this graph and this graph are reflections of each other across the line y equals x. So if you were to draw the line y equals x, I'm going to draw dashed. This graph here is literally just the mirror image of that graph there in that line. And that is always true for things that are inverse functions, is that they are always mirror images of each other across the line y equals x. So the takeaway here, much like last class, is that I want you to be able to graph logarithms without doing too much work. Meaning, I want you to know that just like an exponential function, a logarithmic function has a usual basic shape. And we're just going to kind of manipulate that basic shape.
When you find the log, is it easier? Do you find it easier to make that chart every time? And then like, because I'm just kind of worried that what if I get a log and I can't do it in my head, like figure out what y
Sure.
is?
So to answer your question very generally, I would say actually no. I usually don't make this chart. And I'll give you some examples of both making it and not making it, and I'll kind of point out. But again, here's what I want to say. If you do want to make this chart, here's the thing to keep in mind. The x values you want to pick should be nice powers of your base. So if my base is 2, I'm picking numbers that I know are powers of it, like 2 to the first, 2 to the second, 2 to the third, 2 to the negative 1, 2 to the negative 2, etc. That's what I'm doing. And I'll definitely show more examples like that. But let me first say a very general thing, and then we'll get to more hard examples. So for y equal to log base b of x, where, so I know for exponential functions, we talked about the base being positive and not equal to 1. And that is also generally true for logarithms, but I will be perfectly honest with you. We almost never look at bases that are between 0 and 1. So I'm going to stick right now to the base being just larger than 1. If your logarithm looks like this, so like log base 2 of x, log base 3 of x, log base 10 of x, log base 25, right? Any normal base, I say normal in quotes, we have the usual logarithmic graph. Which is going to be very much like the usual exponential graph, just kind of everything flipped. So instead of having all the usual exponential things, we're going to have all the usual logarithmic things. So instead of a horizontal asymptote at y equals 0, we're going to have a vertical asymptote at x equals 0. And instead of a y-intercept at 0, 1, we're going to have an x-intercept at 1, 0. So here's the general shape for y or x-intercept at 1, 0. And it just kind of looks like that. There is y equal to log base b of x. And just a few notes, the domain is all positive numbers. So you can either say the domain x has to be greater than 0, or you can write it using interval notation, which is everything from 0 exclusive to infinity. The range is all real numbers. Or if you prefer in interval notation, negative infinity to infinity. And I will just point out, just so that you guys can kind of compare, remember when we graphed exponentials, everything was the opposite. So if you're graphing something like y equals b to the x, it's got a horizontal asymptote of y equal to 0. It's got a y-intercept of 0, 1. It's got a domain of all reals.
Did you mean X-intercept or is it Y-intercept?
It is a y-intercept here.
Okay. So are you showing, oh, okay, you're showing us two different.
Totally
Got it.
different. Yeah, yeah. So this is exponential right here. I'm just showing you the contrast because what I really want to emphasize is that literally for these inverse functions, every x and y thing is interchanged. Vertical asymptote of x equals 0, horizontal, right? I interchanged y to become x, and I got an asymptote of x equals 0 instead of y equals 0. And for the intercept, I took my y-intercept of 0, 1 and interchanged x and y to get 1, 0. And the domain and range also switch, right? The domain is all the possible x values, the range is all the possible y values. Those interchange so that all the possible x values here, which is all reals, becomes all the possible y values here, which is all reals. And the range here, which is all the possible y values, becomes the domain here, which is all the possible x values. So I really just want to stress, oh yes, logarithmic functions and exponential functions are inverses of each other. All of the x and y things get interchanged. So to answer, I think I want to say it was Kristen's question earlier, when we're graphing these, I usually want you to just kind of do what I like to call kind of the least amount of work possible, right? You're going to graph it bare bones. Things in order here. So if I was going to graph y equal to log base 3 of x and do as little work as possible, here's what I would want. I know my x-intercept is 1, 0. And then I know it has the usual logarithmic shape, meaning it's going to have a vertical asymptote, which we should write down. And it's going to go up like this. It's going to cross there. It's going to look like that. And now I should point out, it doesn't fully flatten out, right? There is no horizontal asymptote. This does keep getting larger and larger and larger and larger, albeit very, very slowly. We should write down the x-intercept. We should either label it here or write it down over here. X-intercept 1, 0. And then we should also make note of the vertical asymptote. So the x-intercept is 1, 0. The vertical asymptote is x equal to 0, right? It's this line right here. And really, as far as I'm concerned, that's all you have to do. Now, if you were trying to do it slightly more precisely or make a list, here's what you might do. So the quote unquote more precise version, which I don't think is necessary. I think you really can just draw the shape just like we did for exponential functions. But if I want to do it more precisely, I might make a list of things. So if I'm trying to do log base 3 of x, the x's I'm going to pick are going to be powers of 3. So like 9 or 3 or 1. 1 is always a power of every non-zero number. So log base 3 of 9 is 2 because 3 squared is 9. And log base 3 of 3 is 1. Right, so we're always just, if we're doing this kind of thing, we're just picking easy values in the first place. That's a good question. I mean, I would say, well, we'll get there in a minute. How about I'm gonna punt that question to a little bit later in the class just because I have a better answer once we get a little further. But what I would say is it certainly should be, we should be capable of finding these values just by thinking of powers of our base. So 0 is log base 3 of 0, log base 3 of 1, sorry. And then I typically just start taking the reciprocals. Right? Instead of 3, 1/3. And log base 3 of 1/3 is -1 because 3 to the -1 is 1/3. And 1/9 because log base 3 of 1/9 is -2. Because 3 to the -2nd power is equal to 1/9. So I was graphing this in a more precise manner. I would actually draw the little things, which I don't love drawing, but because they just take too much time. So then I would get the point 1, 0, and I get the point 3, 1, and the point 9, 2. And the point 1/3, -1. That's okay. So as you can see, my graph does not always look super great. So, I mean, right, this one or that one, I think that, I mean, this one, okay, is a little more precise, but either one would be perfectly fine. Unless I specifically said to like graph a bunch of points. If you really wanted to graph more points, like if you were saying, James, I don't love this 1-point graph, okay, fine. I would encourage you to graph one more point over here and maybe one more point over here. Obviously, these don't look very to scale, which also is okay. Your graphs do not have to be perfectly to scale. So yes, that's kind of the gist, right? If you're trying to graph this, you're just looking for the general shape. Now, I will point out what's what I'm trying to say here? The larger your base, the longer it's going, the kind of the shallower it is, or the flatter your graph is going to be. So I know it's, well, in fact, let me just use the tools available to me. Let's be smart about this. So I'm just going to point out that, come on, get out of my way here. Sorry. Oh my gosh. Sometimes this computer, okay, there we go. Let me share that. So I'll just say, if you want to do log base, say 2, to do a base, you do an underscore. It does log base 2 of x, and then here's log base 3 of x. Underscore 3, and then you need to push an arrow to make it not be in there anymore. Oops, come on. So what I'm trying, oh God, geez, okay. Oh my goodness. Killing me, I'm sorry, okay. Let me make sure I'm sharing the right thing. Okay, great. Cool. So if you look at this, you can see, oh yeah, the one with the smaller base, base 2, gets bigger faster. The one with the larger base, base 3, takes longer to grow. So the bigger the base, the flatter the logarithm. The smaller the base, the kind of steeper the log. So you can have a base that's like just barely bigger than 1, like I don't know, log base something silly like 1.05 of x. And it's really like, you're like, wow, James, that's kind of giant. But if you zoom out a bit, it's going to start having the usual logarithmic rate. So even if your base is totally wacky, it's still going to have this usual kind of what I call the logarithmic curve. It's the usual exponential curve just turned over. So that's what I would say about that. So you can always expect to have that kind of shape in your graph. And that's kind of a lot of the story, right? If I wanted to graph, say, y equal to log base 5 of x, I would probably just boom, boom, boom. Okay, there's 1, 0. Is it an excellent graph? No, it is not an excellent graph. Is it a good enough graph? Yes, it's a good enough graph. If you wanted to draw it better, you could say, okay, James, well, let me make some marks. And I know that I'm going to get the point 1, 0. I'm also going to get the point 5, 1, right? That's kind of the next easiest point to plug in, is to pick a value of x that's the same as the base. Log base 5 of 5 is equal to 1. Right, so I have log base 5 of 1 is equal to 0. There's your x value. There's your y value. And I also have log base 5 of 5 is equal to 1. There's your x value. There's your y value. So I could also plot the point 5, 1. The problem is that when I do this, it actually feels like it's harder to graph the thing, because you really have to be like, okay, vertical asymptote, and then take a pretty hard turn to get to that point right there, and then maybe make it right. So actually plotting the points ahead of time for bases that are really, once the bases get any bigger than 3 or 4 or 5, things just start looking kind of very, very stretched and scrunched in ways that is challenging to draw. We could label this 5, 1, label this, and we know we have a vertical asymptote at x equals 0. Okay, so something I want to say, let me show you my hand. This is my right hand, and I hope you guys can tell. And I will point out, my hand's not very good. So if any of you want to share your right hand on screen, I would greatly appreciate it. You don't have to, obviously, but if anyone is feeling up to sharing their right hand, the palm of their right hand, it'd be great. So my hand is old and very liney, but if you look, you can kind of see here is an exponential function, which we usually think of e to the x. And here, kind of above the thumb muscle part, is a logarithmic function. Your younger, less liney hands might be much better at showing this than mine. But if you're ever like taking a test, you're like, oh, what does a logarithm look like? You can look at your right hand. Now, if you're right-handed, like many of us are, don't look at your left hand. Your left hand will tell you not the right graphs. But if you look at your right hand, you'll be like, oh yeah, there's e to the x, there's a log of x. Oops, I just did the thing. Okay. So I didn't see your right hand, so that's all right. We can do it later if you guys want. What is the middle line called? Like on my hand?
Yeah, yeah, your hand.
Well, it kind of depends on your hand. Nothing good on my hand, really. But a lot of people have more of like a y equals x kind of line that cuts it in half. But yeah, that's just kind of an extra line that James has and maybe you don't have. So yeah, but specifically, this one here is like a logarithm, and this one here is like an exponential, which is kind of great. Okay. Let's see what time is it. Okay, we got time. Cool. So I will point out for logarithms, usually the base is a positive integer. Integer. 2, 3, 4, 5, etc., etc. Yeah. So there are a couple, so you can have a base that is not like that. Usually you won't see this, but it is possible. We could graph something like y equal to log base 1/2 of x. but it's weird. Because now what you're going to do is you're going to flipping it over the x-axis, right? So let's think about this for a second. I'm going to plot some points to make it easier for you guys to see this. Now, I should warn you all, this probably isn't that important. We could probably just skip it, but I'm going to show it to you real quick and then we can move on. Just because I don't think this will really ever come up, but it could. So let's plot some points real quick. I want some powers of 1/2. Well, I know that 1/8 is a nice power of 1/2. 1/8 is 1/2 cubed. So the log base 1/2 of 1/8 is going to be 3. And if I plug in 1/4, the log base 1/2 of 1/4 is going to be 2 because 1/2 squared is 1/4. If I pick 1/2, log base 1/2 of 1/2 is going to be 1. If I pick 0, sorry, you can't pick 0. You can't plug in 0 to a logarithm. If you pick 1, log of 1 is always equal to 0 because 1/2 to the 0th power is equal to 1. And if you pick something like 2, log base 1/2 of 2 is equal to -1 because 1/2 to the -1 power is equal to +2. So if we start graphing this, let's see what we get. So when x is 1/8, y is going to be 3. So when x is very small, y is 3. And when x is 1/4, a little bigger, y is going to be 2. When x is 1/2, y is going to be 1. And when x is 1, y is going to be 0. And when x is 2, y is going to be -1. And if x were to be 4, y would be -2. Because 1/2 to the -2nd power is equal to 2 to the 2nd, which is 4. So it looks like the logarithmic graph has gotten flipped over the x-axis. In fact, it is indeed true that it is exactly that. Log base 1/2 of x is the same as negative log base 2 of x. You take your log base 2 graph and flip it over the x-axis, and it's the same as doing log base 1/2 of x. It's kind of weird. Okay, so here's what I would say about this. Don't worry too much about this. No one is ever going to ask you really about bases that are fractions like that. On the other hand, there is one other non-integer base that is super important that comes up all of the time. And that base, which we've already talked about in exponentials, is the base of e. So e, which is approximately 2.7, is a very important base. It comes up all the time. And it comes up so often that we abbreviate the logarithm when we write it. So y equal to log base e of x, which has a graph that looks just like any other logarithm. I'll try to be a little bit more precise when I graph it here. So I still get the point 1, 0. And then when x is e, which is about 2.7, log base e of e should equal what, everybody? What's log base e of e? Thank you. Of course. When the base and the argument are the same, the answer is always 1 because e to the first equals e. Oh yeah. So when I make x about 2.7, the y value should be 1. It's going to look like this. And this logarithm gets used so frequently that we abbreviate it as y equal to the natural log of x. You can say ln of x, but I'm going to say natural log of x because that's just the way I am. And a lot of people will say it that way. So whether you write it this way or you write it this way, they mean the same thing. So I need you all to get comfortable with like seeing this and be like, oh yeah, this really just means I've got y equal to log base e of x. No one's going to write it this way, though. Everyone's going to write it that way. So just get comfortable with it. In the same sort of way, what is the domain and range? Excellent question. Well, just like every other logarithmic function, we haven't really changed anything other than the base. right? So for log base 5 and log base 5 and log base 1/2 and log base 3, all of them have the same domain and range. The domain is that the inputs all have to be positive, right? You can't take a logarithm of 0 or a negative number. And the range is every real number. So here, yes, the domain is x has to be greater than 0. The range, all real numbers. And we also have a vertical asymptote at x equals 0. So if you haven't shifted or stretched or transformed the logarithmic function in any of the usual ways, the domain, range, and vertical asymptote and x-intercept never change. They are always these 4 things. Oh, and there was something else I was going to say, sorry. On the other hand, or another abbreviation you should be aware of. Now, I will say, occasionally you'll have a professor that does something different. Generally, most people abbreviate the natural log as ln of x. And most people abbreviate log base 10 of x, which is just, especially if you're taking the 17 series, this is going to come up a lot in 17a. This is abbreviated as y equal to just log of x. And really, it's because people are lazy, right? And well, it's the same thing, but log base 10, we're kind of a base 10 society in many ways. Base 10 comes up a lot. So we decided we didn't want to write or type or print it all the time. So we just said, well, let's call it log of x because it's the one we use the most. So natural log and log base 10 both get abbreviated so that you don't have to write the base. So if I said, what is log of 1,000? You'd be like, oh, James, I know you really mean log base 10 of 1,000. And so then you're saying 10 raised to what power equals 1,000? And we know that 10 raised to the 3rd power equals 1,000. So log of 1,000 would be 3. And nobody needs you to write this part in red here, but no one's going to stop you from writing it either. It's perfectly acceptable to write it. So let's talk about shifting logarithmic graphs, because that's the only other thing I really want to mention when we graph it. I should say one thing, because Kristen did ask a very good question. The reason the domain of the logarithmic function, is everything greater than 0 is because, well, you're taking an exponential and you're switching x and y. So if you take something like y equals e to the x, where the range is all positive numbers. Right? We've talked about something like this. Its graph looks like this. The range is definitely everything positive. If you interchange x and y, well, now we have that the x's are the things that have to be greater than 0. And then if you rewrite this as y equal to the natural log of x, it's still true that x has to be greater than 0. So the reason the domain for a logarithmic function is all positive numbers is really because the range of an exponential function is all positive numbers. Another way to think about it is if you had something like y equals log base 2 of x, and you tried to put a negative number in there. So let's say I wanted to say, like, I don't know, let's find y equal to log base 2 of -8. What you're trying to solve is 2 to the y power equals -8. There isn't a power that makes that true. 2 raised to any power is always positive. This has no solution. Okay, so let's talk about some shifting. Let's say I want to graph, I don't know, y equal to log base 5 of x minus 3. This is going to shift the entire graph 3 to the right. If we look at the original, y equals log base 5 of x, here it is. Beautifully drawn, if I do say so myself, with a vertical asymptote at x equal to 0. This graph here is going to shift 3 to the right. So if I do log base 5 of x minus 3, my new x-intercept, instead of being 1, is going to be 4. And my new vertical asymptote, instead of being x equals 0, is going to be x equal to 3. It's going to look like this. The same graph, essentially, pushed 3 over to the right. There's a couple ways to think about finding these things if you want. If you wanted to find the vertical asymptote, you're really just setting the insides of the logarithm equal to 0. So to find it here, we just set x equal to 0. To find it here, we set x minus 3 equal to 0, which gives you x equal to 3. That's your vertical asymptote. To find the x-intercept, well, how do we always find the x-intercept? We set y equal to 0. So we're really setting 0 equal to log base 5 of x minus 3. And then we're going to rewrite this. 5 to the 0th power equals x minus 3. Anything to the 0th power is 1. So 1 equals x minus 3. And then add 3 to both sides. 4 equals x. That's your x-intercept. That's kind of the more complicated way of doing it. Since it's minus 3, why do you move 3 over to the right? That's an excellent question. I love this question. This one always used to get me as well, because so here's what I'll say very generally. Horizontal things, movements, so both shifting and stretching horizontally. So think back to the trig functions if you can. We didn't do shifting though, we did stretching. Shifting and stretching horizontally usually happens in what I consider a counterintuitive way. Right? You would think, oh, we're subtracting, so we should move to the left, but we're not. We're actually moving to the right. And here's the way I think of it actually. If we're subtracting 3, x needs to be 3 bigger than it was to get the same y value out. Here, x has to be 1 to get log base 5 of 1, which is equal to 0. Here, x has to be 3 bigger than 1, so that when I subtract the 3, I still get the same input as I had over there. So that's why you end up shifting to the right when you subtract on the inside, because x has to be bigger to compensate for the fact that we are subtracting from it before we do anything else. So yeah, subtracting on the inside always shifts to the right. Adding on the inside always shifts to the left, because then x gets to be smaller to account for the adding. Yeah, it's a little counterintuitive. Let's graph a couple more. So let's say I wanted to graph y equal to log of x minus 2. Yep, exactly. Same thing as before, where the stuff inside the parentheses affects the horizontal. So here we're going to shift 2 to the right. So let me start off with, right here would be log of x, vertical asymptote there, intercept at 1, 0. What's my base? My base is 10. So you could plot some points if you wanted to. For example, I could plot very easily the points x is 1, y is 0, x is 10, y is 1. I know it's not a very nice picture, but that would be true. Versus now, if I do y equals log base 10 of x minus 2, I can plot some points here. So now x needs to be 3. So that I have log of 1, which is equal to 0. And x needs to be 12. So that I get log of 10, which is equal to 1. So notice for the same y values, the x values here have to be 2 larger than they were here, which is why this is going to be a shift of 2 to the right. So here's my asymptote that's also shifted 2 to the right. Here's my intercept that is 3, 0. And here's my graph. And again, yes, I know my graph is not very nicely to scale. My graphs are usually not very nicely to scale. So shifting to the right isn't too terrible. Shifting to the left adds another layer of difficulty. So let's look at, say, y equal to log base 3 of x plus 9. This is going to shift us 9 to the left. So our new vertical asymptote is going to be x equal to negative 9. I'm going to draw this one a little more precisely than I usually would. And can anybody tell me what my new x-intercept would be? Instead of being positive 1, what would it be instead? Right, negative James's favorite number, negative 8. So there's my x-intercept. And then the thing here is that I'm also going to have to find a y-intercept. Be careful, you shouldn't cross the vertical asymptote. But there's going to be a y-intercept as well. Luckily, finding a y-intercept isn't too terrible. So our x-intercept is totally going to be negative 8, 0. And the y-intercept, well, how do we usually find the y-intercept? We said x equal to 0. Y is going to be log base 3 of 0 plus 9. Fortunately, this one's pretty easy to calculate. That's just log base 3 of 9, which is how many? It's not 3, it's 2. Exactly. So that's our y-intercept. And that's kind of the whole story. Vertical asymptote is x equal to negative 9. In case you're interested to know, when you shift a logarithmic function left or right, it does change the domain. So here, the domain, instead of being everything greater than 0, now we need to say the insides of the logarithm are greater than 0. So that x is greater than negative 9. Or in interval notation, negative 9 exclusive to infinity. In a similar way, the previous one we did, which was shifted 2 to the right, the domain here would be everything from 2 exclusive to infinity, or x greater than 2. So yeah, shifting a logarithm left or right does change its domain. Okay, let me do one more, and then that'll be it. And then tomorrow, we're just going to review for the final, and we'll also review on Thursday as well. So one more graph for you. Let's graph y equal to log base 8 of x plus 4. So we already know looking at this, it's going to shift 4 to the left. We could write down a bunch of things before we start graphing it. We could say, all right, the domain, we know the insides of a logarithm have to be positive. So we're going to say that x plus 4 is greater than 0, or x is greater than negative 4, or if you prefer, negative 4 to infinity. And we know where the vertical asymptote is going to be. The vertical asymptote is going to be where the insides are equal to 0. In fact, for a logarithmic function specifically, the vertical asymptote is kind of the end or the beginning, depending on how you want to look at it, of the domain. So our vertical asymptote should be x plus 4 equal to 0, or more usually written as x equal to negative 4. That's our vertical asymptote. Well, let's actually start drawing it. So we know we can go 4 to the left. Wow, that's okay. That's good job. Our new x-intercept is going to be negative 3, right? Because we're going to take our previous x-intercept of 1 and move it 4 to the right, and 1 minus 4 is negative 3. If you don't like that, or you feel like it's a little too hand wavy, another thing you can do is say, well, I'm going to find the x-intercept by setting y equal to 0. And if you set y equal to 0, you get 0 equal to log base 8 of x plus 4, which becomes 8 to the 0th power equals x plus 4, 1 equals x plus 4, 1 minus 4 equals x. So x equals negative 3 is our x-intercept. And then it's going to look like this. So here's what I would say, and I always kind of make this mistake when I'm graphing it. Don't start too low. Because if you start too low, you're not going to have enough room to move to the right as you go up. So I might even start at my x-intercept and then kind of draw down to the vertical asymptote like that. It just makes it easy to not make it look dumb. And then to the right like that. again, trying to get that usual logarithmic curve look. It doesn't have to be perfect. It's not going to be perfect. That's okay. The thing that we do need, since we have it, is the y-intercept. And I'm just going to make a blanket statement here. Whenever you're graphing a logarithm, if it's shifted to the left, there's going to be a y-intercept. In a similar way, whenever you're graphing an exponential function, if it's shifted down, you're going to get an x-intercept. So to find the y-intercept here, we're going to set x equal to 0. So I'm going to get y equal to log base 8 of 0 plus 4, which is log base 8 of 4, which is a little bit tricky because this is asking 8 raised to what power equals 4. The answer is not 1/2. 8 times 1/2 is equal to 4. 8 raised to the 1/2 power is the square root of 8, which is about 2.8, which is not 4. So this is not equal to 1/2. How do we find it? Well, there's a number of ways. You could use a calculator, you could do other things. But if you didn't have a calculator, the way you would do it is you would say, okay, well, give myself a little more room here. If I was trying to figure out y equal to log base 8 of 4, I would rewrite it as an equation exponentially. 8 raised to the y power equals 4. And then one of the usual methods for solving something like this is to re-express both sides of the equation as powers of a common smaller base. And I think we did this last time too. 8 is 2 to the 3rd power. 4 is 2 to the 2nd power. Power to a power, you multiply the powers. So you get 2 to the 3y equals 2 squared. And then if the bases are the same, which they are now, the powers have to be the same. So 3y equals 2, y equals 2/3. So our y-intercept is 2/3, which obviously my graph does not look to scale like it's that, but that's okay. So log base 8 of 4 is equal to 2/3. Or expressed another way, 8 raised to the 2/3 power is equal to 4.